Now that's a good cup of coffee. Delicious. What's up, guys? Jonny, Hyman here. It's too derivative. Sunglasses. Welcome to the vlog. How about this? Shield your eyes. It's about to get insane. You might want to shield your eyes. It's about to get cosmic in here. Boom. And then boom, see the Earth. We go fly outside of Earth. We go through the stars, and then we come out through the coffee cup. Alright, welcome to episode 1 of A Verse Making Of. So today, in this video, I'm going to talk about everything that went into making episode 1 of Verse. Not exactly everything, because that actually represents an entire month of almost full-time working on this one video that's 5 minutes long. But I'm going to go into detail about almost everything that I find really interesting and things that I learned along the process and tools that I created to help create the video, etc., etc. Let's get started. So the first thing that you may have noticed, you probably did, and it's very, very subtle. At the very beginning, I say, more often than not, we see the moon in the sky. And that is actually a pretty nuanced statement. The moon is indeed up in the sky more often than not, more often than the sun is, more often than the planets are, more often than the background stars are. But why is that? How does the moon pull this magic? The way that it works is the moon is orbiting at a certain orbital velocity around the Earth, right? Makes sense. We all know the moon orbits. The angular velocity of that, in other words, how fast is it changing, how fast is it going around the Earth in angle per second or per hour per minute, is actually 27 times slower than the Earth's angular velocity around its axis. So what that ends up meaning, basically, is that the moon travels slower in its orbit as the Earth spins. And so it appears to an observer on the Earth to kind of hang around in the sky, to not just stay as stationary as the sun or the background stars do. So that's number one. That's the biggest thing that is kind of interesting. I didn't really notice that ever before until I started making this video. So it takes about 25 hours. It's actually 24.84, if I remember correctly, hours for the moon to go from one point above the Earth all the way around and back. So if you are sitting in the exact same position, looking up, when the moon reaches its peak in the sky, if you wait exactly 24.84 hours on average, you'll see it come back to that exact same point. This is also the origin of when I say a little bit later in the episode, every 25 hours, the moon passes over the same point above the Earth in a very eloquent and careful tone. Now, like a lot of things that I'm going to say today in this episode and that I say in the main episode, there's caveats to all this stuff because unfortunately the universe ain't perfect, and almost every single number that you hear is an average or some sort of rounding on a certain number. For instance, the 24.84 number for how long it takes in hours for the moon to go around to the same point above an observer. That number is an average because the orbital inclination of the moon is not zero. So in other words, the moon does not go perfectly around the equator. And it doesn't orbit in a perfect circle because nothing orbits in a perfect circle. That would be too good, right? It would be too perfect. Maybe there's some star system somewhere, some planet somewhere out there in the billions and the billions that has a moon that goes around its equator exactly 0.000. But that's just not the case here on our imperfect Earth and moon. In fact, so the moon is actually inclined approximately 5 degrees from the ecliptic. And the ecliptic is just what line would the sun trace on the Earth as the Earth orbits around the sun. So it's sort of like this line throughout the year that changes the position of where the sun is along it, that carves out this circle on the surface of the Earth. But the thing is, even that changes. Even the ecliptic changes over time. This is something which I'm definitely going to be talking about in much more granular detail in later episodes because the precession of the equinoxes is the same thing. Basically, the Earth is spinning, right? We all know that. We see it every day, literally. That's the definition of a day. But not only is it spinning on its axis, just like any good spinning top does, it precesses. It does this little wobble, this mini wobble. So in other words, to keep it short, the moon's orbit is not perfectly circular around the Earth, and it's not perfectly inclined at 0 degrees. The ecliptic is not inclined at 0 degrees, and the ecliptic is changing like all the time. So stuff ain't perfect. Moving on. Something that I kept thinking about over and over again as I went out and did all these crazy time-lapse shots, and you know what, can we just have a quick honorable mention for all of those crazy time-lapse shots that I went out and got? I was freezing cold for the vast majority of them. But let's just take a look at them. Can we just take a minute and appreciate that hard work? Here we go. So as I was out there and watching these amazing landscapes and watching the moon move across these landscapes, I kept coming back to this realization that no matter what my brain knows, as I look up to the moon, I constantly am seeing a face in the moon. Always. And it's the weirdest thing. It's happened since I was a little baby kid. And it's actually happened to our civilization and to our humanity since we were a little baby kid. The man and the face in the moon have been a myth and a legend for the longest time because the moon has been around for the longest time. More on that in the next episode, by the way. Something else that I found kind of surprising about the moon, face in the moon and everything is that in the southern hemisphere, Australia, they don't see a man in the moon. That's because if you just look up at the moon, it kind of looks upside down compared to what we would usually look at it as. So they saw other things, like they saw hands in the moon, palms in the moon. They saw a woman in the moon. They saw all kinds of stuff in the moon. The moon rabbit, I think, takes the cake for the weirdest, most imaginative one. If you just look at just what? Moon gazers in Japan see a rabbit making rice cakes with a mortar and pestle. In China and Korea, they see him too, except he's mixing an immortality elixir. Moon rabbits also appear in Mesoamerican myths. So, I guess if there's one thing you can say from this, we have always been a creative bunch. That's for sure. Oh, so buttery. So smooth. Whew. Every single visualization that you've ever seen inside the episode and that you're going to be seeing in this video is actually not made by some crazy visual effects studio, and it's not made in After Effects. It's actually made in a program that I wrote myself. In Python and a little bit of OpenGL and a little bit of VizPy, gluing the two together. And while I was creating the visualization for this shot, where every single planet in the solar system is fit between the Earth and the Moon, which is actually a real thing. You can actually do this. These are all to scale. These are all actual planet sizes, etc., etc. There is a small caveat that I don't think anybody I've ever heard has talked about. The perigee of the Moon, which is the closest point in its orbit, is actually too close. The Moon would be inside of Neptune at perigee. And at apogee, then there's enough room to fit Pluto in between Neptune and the Moon. So you can get all the planets in there, including Pluto, which is a dwarf planet. So for those curious, you have to have an orbital distance between center to center of the Earth to the Moon of 388,124.1 kilometers in order to fit every single planet in between the Earth and the Moon. One more small caveat, this one's a little bit tiny, so I'm going to talk in a whisper for this one. This is all calculated using the mean radii of each planet. This is not calculated using the equatorial radius of each planet. So technically, I don't know exactly what would happen if you use the equatorial radius of each planet. And in that shot that you see, those are not ellipses, those are perfect spheres. So there's a little bit of a caveat there. What are you going to do? Another really fun visualization that was really fun to make was that particle simulation, and actually all of those particle simulations, all to show the gravitational pull of the Earth and the Moon respectively, and to show the tides and the tidal forces experienced by things on the Earth and the Earth itself toward the Moon and toward the Sun. For the scientific minds out there that are wondering why I said the Moon's gravity is only a small fraction of the Earth's gravity, instead of actually giving a number of like what fraction of the Earth's gravity is the Moon's gravity comparatively. It might interest you to know that the Moon's gravity and the Earth's gravity cannot really be compared very simply. There's no real obvious way to compare the two. And all the ways that I could find were kind of just a little cumbersome and a little bit weird. But one way that I didn't really want to put in the episode because it's too many numbers, but it is still pretty interesting, is if you took you, a normal human, I'm assuming you're normal. I'm sorry. I know that might be offensive to some. But let's assume that you are normal weight. Let's say that you are 70 kilograms in mass, okay? So you are being pulled to the Moon right now. If you're an average human, you're about 70 kilograms. You are actually being pulled to the Moon. If the Moon was directly overhead, and it was at its perigee, so it's at its closest position to the Earth. You are being pulled by the equivalent force as 33 and a half feathers stacked on top of each other on your fingertip. You can't stack 32 or 33 feathers on your fingertip. So if you put 33 feathers in your palm right now, just imagine that. 33 typical feathers, actually 33 and a half about. And you imagine how much force that is pressing down in the palm of your hand. That's how much force you would be pulled to at maximum if the moon is directly overhead and its closest point in its orbit. The math on this is actually pretty simple, so here's a quick screenshot of the little tiny Python program I wrote to calculate it. Pretty cool, huh? So that's kind of the fraction of the moon's gravity that is the Earth's gravity, comparatively. So you can kind of get a feel for how much it actually pulls on you and pulls on everything around. The other particle simulation that I did was to showcase spring tides and just the tides in general. So this one's pretty fun. What I'm actually showing here is not gravitational force, I'm showing tidal force. So that is a measure of if you were sitting in the center, in the core of the Earth, which would be a very unpleasant place to be. But just imagine that you could do it on your lawn chair and just have a good time. The amount of gravitational force that you would be pulled to the moon is going to be a certain number. It's going to be a certain value, right? If you contrast that value in that direction of gravity with you being on the surface of the Earth, like say where you're sitting right now, the difference between those two magnitudes of gravitation and the directions of those two vectors is actually what the tidal force is. That's all a very, very technical way of saying that this pretty plot, this pretty visualization is actually just showing you tidal forces. It really highlights that high tide doesn't just occur on the side of the Earth facing the moon, which completely blew my mind when I realized it. But if you look at the visualization, high tide is not just occurring on the side of the Earth facing the moon, it's also occurring on the exact opposite side, because everything's getting a little bit squished, everything's being a little bit massaged by the gravitational force and tidal forces of the moon. And then low tide is really just perpendicular to those 2 points of high tide. It's like a cross, it's that band right across. And it's those two things, the high tide and the low tide and the changing between them as the moon orbits around and the Earth spins, that cause all of those biological effects that we talked about in the main episode. Coral spawning stuff, the gray reef shark stuff, and the land animals' reaction. Now, something that I didn't go into much detail on that I found pretty interesting, I didn't know before, is that lions actually go on the hunt right after a full moon. So this is very possibly the source of a lot of myths and legends and fear that people have had over the generations about going out after full moon, because there used to actually be a legitimate threat. You would be more likely to get eaten by a lion if you went out after a full moon at night. At night, people are most active between dusk and 10 p.m. Thus, most lion attacks occur in the first weeks following full moon, when the moon rises at least an hour after sunset. Consequently, the moon is a reliable indicator of impending danger, perhaps helping to explain why the full moon has been the subject of so many myths and misconceptions. If you're super interested to learn more about the visualizations that I've been making for these episodes, or maybe you want to check out some of the source code, let me know. I want to see how much demand there is for that kind of thing. Every single detail has been scrutinized, and I've been losing sleep over every single technical trade-off with respect to accuracy. Every visualization that you see in these videos is going to be the most accurate thing that I can possibly pull off in a reasonable amount of time. So for instance, this shot of the full moon, this is on December 22nd, the next full moon coming up. Like, comment, subscribe, do all that fun stuff. Smash the like button if you so please, or just gently tap it very kindly and carefully. The next episode is going to be completely insane. We're going to be talking about the origin of the moon. There's going to be all kinds of ridiculous VFX shots that I'm kind of internally horrified as to how I'm actually going to do them, but incredibly excited about what I might learn along the way. So stick around, and I'll see you in the next one.